mistakes are permanent, but don't let that make you nervous.
We'll just put all the bloopers up on
If it's really bad,
We'll make a blooper montage at the end, you know.
All the boats crashing.
So we're ready to start.
Sure. Okay, please.
Well, hi. We are the Albuquerque, New Mexico. What's their name? The Desert Dogs. They named it, so I don't even remember the name sometimes. So I'm Ensign Blemmel, and this is Hyunju Blemmel. We are students at El Dorado High School at Albuquerque, New Mexico. I just finished my freshman year, and she just finished her junior year. And this is my dad, Peter Blemmel, and he's a student of the University of New Mexico.
Okay, page down doesn't work. What do we have to do?
Oh, there we go.
Okay.
But first, I want to say that for my AP Physics class, instead of taking a final, we were allowed to do a final project. So I actually chose this, so I was able to use class time to work on our project. So I wrote a technical paper, and I'm going to pass those around real quick. I have some copies. Pass around.
Alright, so we're going to give you a little idea of the process we went through to get everything in motion. So we started at a whiteboard, and we just started working out the design control theory and just how the system was going to work. And then we went out and we bought and assembled everything we needed and built ourselves a brass board. So from there, we wrote the software. We tested the software using some of the brass board and the indoor fans. We assembled them onto the solder and onto the cape. We got our spare processor and cape. We built them. She wired them up. And we calibrated the compass and test GPS in the parking lot. And I kind of just went around to the parking lot corners with my dad's phone and took GPS coordinates and used them as waypoints. So we sort of got our fake buoys out of that. And we tested them in our city's sailboat pond, which is 2 feet deep and 20 feet wide.
A little bit. How much?
So between the three of us, we have a lot of experience in robotics and mechanics. So my sister and I participate in the El Dorado High School After School Robotics Club. She is the president of the robotics club. We both compete and volunteer in the RoboRave International, which is a competition held in Albuquerque, New Mexico. I took middle school division first place 2 years, and she took third place high school 1 year. And now we volunteer and help run the show. Also, we have been to FTC, the First Tech Challenge, and done that challenge there. So, by trade, my dad, Peter, is a professional programmer in artificial intelligence, so that was kind of helpful in getting the autonomous robot going. We have a lot of experience in construction, like small-scale construction and hardware engineering, and apparently we're also very enthusiastic and So a few of our little design considerations. We were under a limited budget. We're trying to stay under $750 as we have limited sponsorship. We have absolutely no experience in boats and sailing. We have very limited access to water, in deep water. We don't have a chase boat, and the only ponds we have are big enough for 1 meter boats, so that restricted us. And and getting everything here was also a pain. The boat and So this is our boat. It is a Vela 1 meter. It was picked out by her after the 2013 sailbot. She went out and saw what everyone else was doing and tried to get as close to that as possible. After we got the kit, I assembled everything myself, got the rigging, the masting, all that fun stuff.
So, as Ensign mentioned, he's not completely inexperienced because he's a Boy Scout, and they get to put sailboats and canoes on a pond, but that's about it. That's all we get to do. So we took the KISS principle where we kept it as simple as we possibly could. And so in the sailboat manual, They had this little chart of how to set your sails based on the wind, and that is exactly what we did. We built a little table of data. We kind of looked at it and said, well, it's approximately, that looks like they got their sails about 45 degrees out and maybe about 20 degrees out in each position. So we simply built a little data table, and we did the same thing for our rudder. A little simpler, but so this is really it. Basically, I have a little more complicated control diagram to show, but the long and the short of it is, we have once we know the apparent wind angle to the boat, we just look up that angle in this table, which is about in roughly 30 degree increments, and set the sails. And that worked actually pretty good out there on the water for us. So the encoder is a magnetic encoder, which Angie will talk about in a little bit. It takes our current relative wind direction, the heading that our compass tells us. We take our angle to the wind, out of that comes our angle to the wind, and then a quote-unquote true wind direction, which we can't really compute because we don't have a wind speed sensor. But then we know where the marks are, and we set a waypoint about 8 meters or so past the mark as our waypoint, so we don't turn too early. We know what our GPS position is. That gives us the distance and the angle to the waypoint with some very simple mathematics, some high school level mathematics. We take that in and we compute what we want our new angle to the wind to be. As everyone else has mentioned, we can't sail into irons, and so we compute what we want our new angle to be. So everything is based off what we want our angle to the wind to be. And out of that comes our rudder angle and our sail angle. Our system is really pretty simple. It talks to the commercial rudders and the servos that came in the kit, and those are pulse control modulated, PCM. And all we have to do is compute the duty cycle for the position that we want on the rudders, and that comes out of that software block. And we have a little bit of compensation built into it in a feedback loop where we know where we previously were in its position in time, where we think we were supposed to be in position in time, and out of that comes out an error based on where we are right now in position in time. And so we have a little bit of auto calibration going on as it sails along. That really proved to be helpful in this particular competition. We had not anticipated the current that's out there, and our boat, it gets actually pushed aside by the wind, which we hadn't counted on. So instead of just sailing, it's actually being pushed around from different directions. So did I just skip twice, or are we good?
We're good.
Okay, so that's you.
So we had a couple different components. This is basically everything that we pulled together for it to work. We used a beagle bone, which we talked to through Wi-Fi. We had a cape, and that's what you stick on top of the beagle bone. This is it, and the top will come up. And then we soldered on a bunch of different parts, including the GPS, the compass, the encoder's at the top of the boat, and there's a voltage divider on here. You can see I soldered in little resistors, and it's all powered by batteries, which we hook up on the inside. And then that's all talking to the controller that came with the boat. So, pass this.
That's the actual module that we're sailing with, so you can't keep it. But we have a spare. So what you're actually looking at there, just if we sort of take a high-level block diagram approach, the boat came with a receiver, and that receiver already talked to the rudder and the sail, obviously. We bought from the Palalu website a MOX that takes a third radio control channel and switches between the master and the slave inputs. We hook the processor, the Beagle, up. Its PWM outputs go to the slave side of the MUX. So rather than, unlike the other team, rather than doing this in software, it's just a switch on the radio that tells the boat whether the computer's supposed to be in control or we're supposed to be in control. As everybody else has mentioned, things have been very, very dynamic out there on the water. We discovered that the receiver was shorting, or appeared to be shorting, and kept browning out the processor. So we now have 2 batteries and 2 voltage regulators in the boat. One battery. This MUX is actually, it takes all of its power for the servos from the master, and it ignores the power from the rudder, from the from the beagle bone. It just uses the PCM signal. So we have a couple of, again, everything's off the shelf. We try to stay cheap, and these things are like $8 a piece. So these are our voltage regulators. They convert the 3.7 volt battery up to 5 volts. And everything kind of tucks into the hold, except for the beagle bone, which she'll show you in a minute, is up on the top of the pool. So I'll let you.
So basically, we started with the Raspberry Pi and the Arduino, but right after we started using it, we switched. We switched to the BeagleBone Black and Cape, basically because of size, power, and weight. It requires a little bit more programming, but because my dad knows how to do that kind of stuff, it wasn't as much of a problem to us to switch. So our electronics all use different voltages, so basically we did voltage dividers through resistors. So the encoder sends out a 5-volt signal, but we had to divide it down. So with the resistors, it's able to send to the board a 1.8-volt signal. Now it's able to solder it on the board.
Yeah, you can see a couple of resistors there on the top of the board that she soldered in.
So the GPS and compass were soldered on. You can see it just like this. This is the GPS and this is the compass. We made 2 capes in case one of the first ones shorted out in the water. Hopefully that wouldn't happen. And actually on the second cape that I made, the compass didn't work. And so by the time we had soldered it on, it's really impossible almost to take a whole row of pins off. And we looked it up and it said basically you have to heat blast the entire thing, and that would have undone everything. So up there you can see the resistors are in an L shape. So we changed that to a line down here, so that way we could put 2 of them side by side. So this one doesn't work, but it looks cool to the inside.
Okay, inside.
Alright, so when we were dealing with calibrating our compass, we ran into a few hard and soft iron issues. Those being a hard iron issue is where you have a solid chunk of metal somewhere that's throwing off your compass. I'm sure you've all had to deal with this if any of you were Boy Scouts. And then we also have soft iron errors, which come from the internal electronics sending current, which creates just...
Yeah, you may not be able to see this green from the back of the room, but basically your magnetic field is supposed to be a nice circle around your compass. And what they've drawn here is the soft iron errors cause that to turn into more of an elliptical shape. That green may not be visible from where you are.
Yeah, so with the hard iron errors, it takes it off the origin, your circle, and soft iron, it compresses the circle. So this is the data from a few of the tests we ran earlier. So we quite literally took the box and stood outside and started turning it to all 3 axes, the X, Y, and Z, and just started collecting data. So here, I don't know if you can see this, but this is the raw data here. So it's off the origin and it is compressed. So after compensating for the hard iron, it's still compressed, but now we have it on centered on the origin. And after dealing with that, you end up with a somewhat nice circle. So using a bit of 4th grade geometry and a ruler, I devised this little compass sheet here. It is just a sheet of paper with an origin and bearings. So we use it to calibrate the sensor. So because it's not mounted north to south on the boat, it's just on there. You have to figure out which way it's facing.
If you look at on the board there, that board north to south is when that little black chip is pointing that direction, and we've mounted it sideways on the board. So it's not north to south in the first place, and then of course it's whatever it's doing on top of that.
Yeah, so we just put the box on there and start turning it to certain directions, and that's how we calibrate the compass.
So the encoder is basically a magnetic shaft encoder. You can see up here there's a little bit sticking out, and as you turn it, it sends a signal back to our computer, and you can read how far it's turned. And to waterproof it, we stuck it inside a chapstick cap and put some Vaseline around it, and it was waterproof. So you can see that there's this cable, and that runs all the way up the entirety of our mast. Our first thing that we stuck on there, we just took a piece of plastic and tape and used it and found out that that didn't work very well. So we went ahead and made another one. You can't really see it.
Coffee stir sticks.
So it's a coffee stir stick and some more plastic cut up in tape, and we kind of just stuck it on there.
So as Shenji mentioned, it talks Wi-Fi, but it doesn't talk Wi-Fi very well when it gets out of range out on the water. So when we're on the water, we plug into the computer, we talk through its console port, which is the little black, you certainly can't see that black circle from the back of the room, but where that little bundle of orange and yellow and brown wires is. And then we disconnect it, we set it in the water, and we can't talk to it again until we pick it back up out of the water. The battery box, my company has a little 3D printer, not a very expensive one. So the hold of the boat, these Velas, they come with a nice little balsa wood, I don't think it's balsa, but it's some sort of thin, lightweight wood. We gouged that out, but left enough of it intact for it would hold the servos, because we needed the torque structural stability. And then we just 3D printed a little battery box to stuff it into. So this is just kind of a picture of our what they like to call a roadkill board. Started with a brass board and threw everything together. We're running a little short on time, but if you want to talk about it for a little bit, you can.
Well, so before putting everything on, we wanted to make sure it worked, so that's what the breadboard was for. And his company has a lab that we used, and we used their resources. I think that's mostly it.
So this is a bit of our indoor testing stuff we did. We set up 2 industrial barrel fans on a desk, because that's basically the most wind you can get in New Mexico.
Well, that's not true. But it's
Inside.
So we have our boat here, and on top of there is our sensor, and we have the servos set up. So with the wind, we kind of get the tilt we're looking for in the calibration, and we can start dealing with the sail angle and the rudder control.
Then we went to the parking lot. That's outside.
We did a lot of work in this parking lot.
And that was so our GPS could actually get signal and our compass wouldn't be thrown off by the inside, being inside. But basically it was the same as inside but outside in the parking lot. And this is our pond. As you can see, he was standing here and you can see the other side. And the dock is going faster than our boat.
Yeah, the ducks were, we didn't have a lot of wind to work with. So then you were going to talk about the repairs you had to make.
Oh yeah, so the boat comes with these little cotton lines that you have to rig it up with. And basically the 3rd day we had it, the sail rigging broke. So we got out some 30-pound test braided fishing line and replaced the rigging with that. Mainly the control for the sail angle, because that's set to a wind, and so we did that. And also, the moment it got to these Newfoundland winds, all the swivels broke off. So we went out to a fishing store and got some.
When we say we, that's the royal we. My wife has been doing nothing but running to Walmart.
Yeah, so we replaced all the swivels on them, and some of them I just doubled them up because we didn't have enough.
So our basic acknowledgments is management sciences for funding. Our schools don't really even know we're here. We just kind of said this is where we're from, but we just say we're from there. And the rest are the people from work who taught us how to do things and helped us out, and then our mom for driving us. She's so great. She's the best. Love you, Mom.
So I'd like to close by saying that obviously I've been mentioning that I'm a software engineer. I'm one of those guys who back in the beginning of the dot-com boom, the money outside the university was better than the money inside. So I never finished my degree, and I'm back in school right now. So I understand the spirit of the competition, but I am actually working on my undergraduate degree finally at the University of New Mexico. But it does give us a little bias in the software world that I have a number of years' experience. So however you want to factor that in, that's kind of up to you guys.
And New Mexico is in the United States.
Yeah.
It's not Mexico.
Mexico right here, it's we like to call it that little hole between Arizona and Texas.
No one, people in the States don't even know where we are. Like, you're from Mexico? No! Where are you from?
The nearest ocean is 12 hours away.
Okay.
We live here. And the ocean is like everywhere else. Yes.